So, good afternoon, and it's a pleasure for me to have the opportunity of giving this webinar for Rilem on digital concrete. I've added as subtitle questions, dream or reality, new green or ecological monster, and I will try to address those questions throughout the talk. As an overview, I will start by explaining why we can have an interest in doing digital fabrication with concrete, how this can be done, what are the challenges, and whether digital concrete is sustainable or not. The first point I want to make is that there are a multitude of projects dealing with digital fabrication with concrete, and some of them shown here more recently are really reaching large scales and relevant applications. To get an impression on the growth of digital concrete projects over the years, I show you this graph from a paper by Buswell and co-authors showing essentially an exponential growth of projects in this field over time. But the question we want now to deal with is, why do we really want to use digital fabrication, and in particular, digital fabrication with concrete? Well, I would say that if we go back to the very initial motivation, this has to do with CAD programs making it possible for architects to design all kinds of novel, interesting, and more complex structures, but that the ability to build those structures was not there. And the question then is, can advanced manufacturing and robotics offer a possibility to change this situation? Can robotics be used for large-scale manufacturing in the construction sector? I would argue that there is also a newfound motivation, and this has to do with sustainability, and I want to see whether this is credible and in what circumstances it might become credible. And to look at this question, let's use this very simplified equation, arguing that the total impact of building a structure has to do with the amount of material used, the material impact, and the service life. So, from a material science point of view, we can, for concrete, look at making concrete with lower clinker contents. We can use recycled materials. There are also possibilities, I believe, in earthen construction, where we could use materials with very low environmental footprints, but there's a number of questions there also that have to be dealt with. The service life is clearly very important, and here the material science of durability is a central topic that needs still further research. There are aspects of designing for reuse and for recyclability. Here, in general, the development of performance-based standards is clearly very important. And then in this region here is where digital fabrication can play a role. It is about smart design. Lean construction, I would argue, better stated, construction using limited amount of material resources. Here also, I think that digitalization can help to have better structurally informed shapes, but also plan for reusability. All of these aspects actually connect to each other, and in particular, if you're going to change a material, for example, for digital fabrication, you would certainly not want it to shorten the service life. Very far from digital fabrication, and as an example of a long service life with a good material design, is our reference structure of the Pantheon, where material science, but also good engineering, has been used effectively and led to this very long-lasting structure. Later, we have, for example, here, the King's College in Cambridge, a very impressive vaulted structure using minimum amount of materials thanks to a very smart design, maximizing compression forces and giving a vault which is using only minimum amount of stones. Now, this has been an inspiration for a number of architects, and I would in particular like to underline the work by Pier Luigi Nervi this ribbed floor system, think about it as some kind of waffled structure. And here the interesting part is that at the time when this was built, labor was cheap and the material was expensive. So these types of structures made economical sense. However, today it is expensive to produce them, and therefore we go to structures that are more cost effective to produce with limited amount of labor. And the topic of digital fabrication is whether such structures that use limited amounts of materials could be revived thanks to novel fabrication processes. This is an inspiration for a variety of modern architects, including Professor Bloch, a colleague at ETH. And here you see an example of a funicular floor, a functional ribbed floor system that he has designed and actually built in the high-low at EMPA very recently. So where does this leave us? Well, as summarized in the paper by Dr. Wangler and co-authors in CCR 2019, for ordinary construction, we would have a cost versus complexity going something like this, with a strong increase in cost as the complexity increases. For digital fabrication, we start at a higher cost for elements of low complexity, but the additional complexity comes at very little extra cost. And this gives us a break-even point here, where beyond it, it becomes cost-effective to construct digitally. However, what we have to do through research is to reduce the price of digital fabrication, make these processes more effective, and in doing this, we shift the break-even point to the left, and we are increasing the range of structures that are cost-effective to build. We make it more cost-effective to build using less material. And this is where a lot of benefit from research and development is expected. Having seen the motivations for digital fabrication, I would like to develop now an overview on various processes to fabricate digitally with concrete. And the pioneering work here comes from Professor Koshnevis at the University of Southern California with the process of contour crafting. This is a process of extrusion printing, and it really came onto the front scene of most world newspapers with the accomplishments of the Winsun company in China, which in particular printed 10 of these houses in 24 hours and created a mega worldwide buzz. Since then, a variety of products have developed or are in construction. Here you have this pedestrian and bicycle bridge at Eindhoven, and here a project of a house development, which is also being done by our colleagues at the University of Eindhoven. Here is an example of columns that have been printed in exotic shapes for a scenario of a dance spectacle in the Swiss Alps. This was actually a proof of concept for a tower that we are in the process of planning now for 25 meters height and quite an exceptional architectural design. Another process is 3D printing in powder bed printing, pioneered in the construction field by Enrico Dini and his company T-Shape. The idea here is that you lay down beds of powder and then pass with a giant inkjet where you squirt a liquid at the places where you want the powder to harden. And once you have finished, you remove the unsolidified powder, and this gives you the possibility to have such objects with relatively unconventional and difficult otherwise to produce geometries, in particular in terms of overhangs. The process has been used on a large scale to produce this pedestrian bridge present in Madrid. I have to say that it is supported by a steel structure, but for a first of realization, it is, I think, something that we can consider as quite acceptable. To highlight the level of resolution that powder bed printing allows, I would like to show you this object here, the Digital Grotesque 2, presented at the Centre Pompidou in Paris. And here is a zoom on the level of precision that you can get. Of course, the question is, why would you want this? Well, in fact, you can have aesthetic reasons, but there can also be objects that are more complex to realize because of overhangs, because of cavities, and all of those situations are ones where we could find an interest for digital fabrication with this process. An option is actually to use this sand bed printing to produce formwork for concrete. And an example in the resulting shapes is shown here. These are elements of a post-tensioned slab for the DFAB house in EMPA, of which you see a picture here, and for which I invite you to visit the website. Inside the first floor of this house, there are a variety of concrete objects that have been produced with different digital fabrication processes. Here you have this roof where the mold was produced by powder bed printing. Here is a so-called mesh mold where a robot has created a rebar cage out of steel that is then filled with concrete. And here we have columns, mullions actually, holding the windows, and these are produced by so-called smart dynamic casting. The first version of this smart dynamic casting is shown in this video. As the robot moves up, this mold section here gets filled with concrete, and once the concrete is released, it must be stiff enough to support the material on top of it, and over time, its strength must increase to carry the additional load. Now, this process made us think about another option. It is to use a very weak formwork, something that might be simply 3D printed in a recyclable plastic. An example of this is shown here, and the interest in this approach is that you can produce relatively ordinary reinforcement systems that are easy for an engineer to approve. And therefore, in terms of structural integrity, you have a much simpler situation than for extrusion printing. And I will get back to the notion of structural integrity at a later stage. Now, this object here is a concrete column shown here, produced in our lab, and serving as a base for this future tree, a pavilion at the renovated headquarters of the engineering company Basel and Hoffmann near Zürich in Switzerland. The same type of process has been used to create this exotic post-tensioned structure out of 3 elements, and I like to show this object to underline the geometrical complexity that this 3D printing of a formwork allows us to access with concrete. However, this 3D printing of a formwork takes time, and you might argue that it generates also its load of waste. So let's look at even easier systems. And just about as cheap as it gets is a plastic foil from the supermarket. This video shows you the process that we refer to as admixture controlled digital casting. And what you see is that the concrete gets cast into this plastic formwork, which does not deform. It does not deform because there is an accelerator added here in the nozzle, which helps the material, as soon as it is deposited, to stiffen enough and avoid any substantial hydrostatic pressure from developing. So we have seen various possibilities of fabricating digitally, and now I would like to cover briefly some of the challenges to do so. Among the different processes that I have presented, many of them have a certain number of commonalities. One of these is that the concrete must be pumped, so it has to be pumpable. The concrete should then be delivered in place and hold its shape. This is something that we could refer to as the concrete having to be placeable. However, as you progress in the building of your structure, the strength of this concrete must increase, and therefore we have the requirement of a property that we can refer to as buildability. This increase in strength, this buildability, is more easily achieved if we use an activation of the cement hydration to get strength not just through thixotropy, but also through hydration, and I would say mainly through hydration. Meeting all of these requirements is a challenge, and it is at the center of the art of formulation of digital concrete, and clearly the use of various chemical admixtures is a great help to achieve these objectives. To elaborate on these objectives, let me just underline that in extrusion printing, we're talking about completely suppressing a formwork and needing a material which is self-supporting as soon as it is placed. In the processes of digital casting, there may be some minimum initial support, but very rapidly also the material should build up strength. So in both cases, the process of so-called setting on demand, of accelerating the material as it is deposited, is very beneficial. And in order to optimize our systems, we need a conceptual understanding of these processes, but also measurements to follow this strength development and better calibrate it to the needs of a given construction process. Now, in terms of setting on demand, let me explain very briefly how you may think about it. Imagine that you have these people representing cement particles, a lively lot that you would initially like to calm down. And for this, you might use a set retarder. In this case, we might think of tequila, which would have the effect of putting these guys or this cement to sleep. At some point, and in digital fabrication, this point is the moment where you're going to be placing the material, you would add an activator, and you could think about this as coffee or Red Bull or something like that, which would wake up this group, which would wake up the cement and cause them to start hydrating, developing strength, and having the ability of supporting the additional layers that get placed upon the freshly deposited material. So this can be done in various ways. You can use digital casting, layered extrusion, but also the spraying of coatings. All of these essentially rely on some degree of retardation of the concrete, depending on whether you prepare large batches or you have a continuous mixing system, and an activator. This goes through a mixing chamber, the material gets placed, it starts to hydrate and develop strength. This concept is essentially what you will find in different types of patents for such mixes, and I don't want really to go into the details here other than give you some references in case that is a subject you are interested in. From a conceptual point of view, I would like to point you to this reference paper by Wangler and co-authors in Rilem Technical Letters. And the idea here is that we represent, in terms of concrete height, the load-bearing capacity of our concrete. Now, initially, and only through thixotropy, we would only be able to carry a height of about 50 to 70 centimeters, plus minus something, depending on the details of how you do it. But then we have a period where the material is not going to harden, and where if you don't do something to develop strength, the level of height that you can reach is very limited. This is illustrated in this video, where you see that if a particular height is reached, then the material below it starts to collapse as additional layers are tentatively deposited. So this is where we need this set control, this setting on demand that I was defining previously. The question of developing a digital fabrication process is how to measure this. And for this, I would briefly like to point to some work, in particular in the PhD of Lex Reiter and in the manuscript in preparation, where we use penetration techniques, either fast or slow. And essentially, from the resistance to pushing a needle in the material, you can get a strength over time. You see that the depth of penetration does not have a big impact on the result, but that as time goes by, the strength increases. And this is essentially what we want to measure. But you could just use a single needle and push it only very slowly into the material. And if you do this, you get a reproducible process with the same increase of strength over time in your different mixes, and the possibility to have a continuous characterization of the strength buildup of your material. So a very useful method that I will show you some uses of shortly. Finally, I come to the question, is digital concrete sustainable? So a couple points. Most digital concrete has to be pumped. Because of this, we have to remove the coarse aggregates, and this increases the volume of paste. Apart from this, because of the need for a rapid strength gain, there has been a tendency, in many cases, to get a little bit of that strength through the reduction of the water-cement ratio. And this also increases the clinker content per unit volume. And this enrichment in clinker content of concrete is something that you need to compensate somehow, in particular by designing structures that use less material. But the more you have an excess in clinker, the more difficult this will become. And therefore, it is also important to work on the material, for example, by including supplementary cementitious materials in these concretes used in digital fabrication. Here, I would like to give you an example from a recent publication where we used a blend containing only 50% OPC in the cementitious mix. What you see in the first graph are ultrasonic measurements that are used to give an indication on how the different accelerators used are capable of activating the hydration of this system. And what you see in particular in the insert is a very good ability of these accelerators to increase the early strength gain. In terms of compressive strength, the good news is that using these accelerators does not modify the compressive strength that you get from 2 to 28 days. So we can use these systems, we can activate our blended cement, but very importantly is, will this printed blended cement be stable during the printing? And the answer is yes. We've used an approach which is detailed in that paper, using the type of penetrometer measurements that I referred to above, defining rates of strength gain that are needed depending on the rate of vertical printing. And from these measurements, essentially, we could identify situations where our printed material would be hardening fast enough to print vertically a column at a very decent rate. So here is an example of the mix design. Here are some pictures of the printed material with 300 kilos of OPC per cubic meter, very similar to a relatively good ordinary concrete, still high with respect to highly blended concrete, but still with a reduction of more than a factor 2 with respect to previous mix designs that were used for 3D printing of concrete. Big remaining open questions in the field in a more general scope are, will we be going for on-site fabrication or prefabrication? Are we going to target unreinforced masonry or reinforced concrete? Are we going to go for high-end structure or ordinary construction? What is the reliability going to be? In particular, the structural integrity. I underlined how in some processes it is much easier to incorporate normal steel reinforcement and have it an easy task for an engineer to sign off. The more involved the checking has to be, the less market relevant the solutions will be. The higher will be the cost, and the more difficult it will be to penetrate the global market. Sustainability. I underlined the reasons why many printed concrete formulations have a high clinker content, but I also showed that a lot of improvements are possible. Key questions here are, what are the benchmarks going to be? Does the durability change in these printed concretes? What is their environmental footprint? And in particular, how should we compare that to relevant benchmarks? What are the costs going to be, and how will the market react? If we come with a very threatening solution into the market, ordinary processes are going to adapt. And I think this is something that we should not forget. So in conclusion, and as I like to tell my students, think different and build different, but build safe, durable, eco-friendly, and cheap, or cheap enough. There are many requirements to address. There are many disciplines that are needed to do this successfully. So interdisciplinarity, I think, is particularly important in digital fabrication. And I would like to leave you with this slide, which underlines the need of this interdisciplinarity. And with this, I would like to thank you for your attention. In particular, I would like to thank the Swiss National Science Foundation for having funded the National Center for Competence in Research on Digital Fabrication, from which I took many of the examples that I showed you throughout my talk. And with this, I would like to leave you with some references for the Digital Concrete conferences of 2018 and 2020. There are special issues in cement and concrete research. There are also conference proceedings and recording of many of the talks, in particular the invited and keynote lectures. Finally, let me underline that there will be a conference, Digital Concrete 2022, that will take place in Loughborough. We look forward to seeing all the community there and hopefully some additional enthusiastic researchers contributing to this field.